Thank you very much for joining us today at this webinar on being a computational social scientist. This is part of a larger UK data service training program for social scientists wishing to learn about new forms of data, for example, data from the web, social media sites, text mining, things like that. First, we hope everyone is well under the current difficult circumstances and that you're joining us. We really appreciate that you're joining us during this challenging period. So just to let you know, we have upcoming webinars on text mining, both an introduction to the basic concepts, text mining basic processes, so some of the really fundamental and most commonly used text mining methods, and then advanced options with a little bit more difficult things, a little bit more specialist. We also have coding demonstrations on the 13th and the 20th. Those are focused on web scraping and APIs respectively, and we have past webinars that you can watch again on the UK Data Service YouTube channel, where we keep videos of past events. To dive right into the meat of today's episode, let's begin. Computational social science is a very interesting field, and the aim of today's webinar is to demystify what we mean by computational social scientists, argue why it's worth your attention, and give you some tools and some methods for how you can get into it. So our table of contents covers what is computational social science, why be a computational social scientist, how to become a computational social scientist, and the big 5 concepts that you need to know to be a computational social scientist. There'll be time at the end for questions, and then we'll have some links to further materials that may be of interest to you. So fundamentally, what is computational social science? We start with the basic question, and you might think, all right, is it scary? Is it interesting? Is it confusing? Because really, isn't most social science already dependent on or supported by computers? Yes, it is. We all do, code our interviews in NVivo or something like that. We build statistical models in SPSS or Stata, and we conduct our research online through, online surveys or online interviews. We do a lot of things. We share files. It's great. But computational social science is not just using computers. It's using computational methods to answer social science questions. So, for example, we would use computational social science to address big data, to write code, to apply analytical methods from other disciplines. For example, we might look at how social networks, they can be mapped by talking to people and asking them who's in their network and who they speak to most, or they can be mapped by scraping large amounts of data off of a social networking site and building graphs that show how much these people interact on that website. Those are both valid methods. They both will come up with different answers. Computational social science has advantages in certain ways. And we'll explain what those advantages are because we think you should become a computational social scientist. Computational social science is an opportunity. That's the biggest reason. The known universe of data is expanding rapidly. Vast swathes of our daily life, our social interactions, our activities and our behaviors are captured digitally. And it's a very, very interesting resource. If you can use all of that information that's captured, if you can amalgamate it, if you can put it into resources that you can approach as a social science sort of mindset to how to use those resources. So there's websites, documents, records, images, corpora, algorithms. But beyond an opportunity, computational social science is a methodology or a toolkit for working with data. That covers, processes and approaches to large-scale or unstructured data, how to capture data generated or published in real time, how to access information on new or previously unmeasured activities. For example, things that are only online could not have been measured previously to computational social science methods. Also, how to access information on familiar or existing things, but at different scales or in different ways. And, empirical social science is having its moment in the sun. We can use the theories that have been developed and really test them. We can put them to the test, we can modify them, we can generate them, we can do some interesting things. So the question is how? How do you become a computational social science? Start off by being a social scientist. This is because social scientists already possess knowledge and skills and training around how to categorize and code responses, how to evaluate data quality, how to infer, patterns and important concepts from massive amounts of data. These are all skills you will need as a computational social scientist. You just need to layer on a little bit of computer skills and you're good to go. So what are these computer skills? There are a lot of them. Some of them are very specific, some of them are very general. We won't go into everything here, but what we will say is that you will need to do things like write programming scripts. You will need to employ analytical techniques. You will need to use good tools and best practice to structure and document your research. And really, what we want you to focus on are the big 5 of computational social science. They are thinking computationally, writing code, knowing your computational environment, understanding and manipulating data, documenting and enhancing your workflow. I will cover number 1 and number 5, but I will pass it off to my colleague Dermot, who will cover 2, 3, and 4. So, number 1, thinking computationally. This one can sometimes be the most difficult because it's a little bit meta. For example, we need to be aware of what are human problems. Human problems, or indeed living thing problems, like staying alive, involving responding to danger, fast danger like wolves, but also slow danger like dying of thirst. Curiosity about the unknown, so that we know, is this dangerous? Is it useful? Recognizing patterns. This helps us respond better to danger or resources around us. So we have to be able to recognize, for example, whether a set of footsteps is a dangerous animal or a person that we know or a completely new thing that we've never seen before, and we should be curious about it. Now, most of these kinds of thinking, and they are thinking, are not what we usually understand thinking to be. These are more instincts. They're not irrational, they're sub-rational because they happen much too quickly for us to think about consciously. But sub-rational thinking is just thinking. There are some other human problems. For example, other people. I don't mean like, oh, that one, what a problem. What I mean is we have to navigate a world in which lots of other people are all doing their own thing, and we have to be able to respond to them and understand them. For example, by understanding intentions. This picture, for example, really quickly, like super fast, we understand this as play fighting. Now that's different than playing with blocks, but it's also different than real fighting. And we have to use that information to predict likely responses. Are we going to have to intervene in this play fight? Are we going to leave it alone? Or we have to know how to respond. We also have to understand these things, the intentions and the likely responses, in the context of wider networks of human interaction, things like collaboration and competition. So solving problems relating to other people draw on the same sub-rational thinking that we saw in responding to danger or recognizing patterns. We read faces and interpret situations and sort of read the room really quickly, like much too quickly to think about consciously. And so this highlights that human thinking has co-evolved to deal with human problems in several ways. We have limits on our working memory. We can really only focus on between 1 and 7 things, and it's only one thing if that's a complex thing or if it's an unstructured thing. We do have some workarounds. For example, we can use chunking as a way of turning large quantities of unstructured data into smaller chunks of semi-structured data. someone gives you a phone number to remember and you can't write it down right away, you probably remember it in blocks of 3 numbers or 4 numbers. And that's easier to remember than one string of individual numbers. It's just how our minds work. We also use bounded rationality. We do not, when evaluating a situation and trying to find a solution, really look for the best solution. We look for a good enough solution, and we find it quickly, because quickly is more important than best most of the time for human problems. We use a lot of that's satisfying, finding a good enough solution. We use heuristics, rules of thumb, to help us find those good enough solutions quickly. So if it's got feature X, then we treat it like feature Y, and that's good enough. Very fast. We also have communication assumptions. Basically, we interpret other people as likely to respond the way we would respond if the situation were reversed. So we kind of interpret, we assume other people also separate objects and actions, and that they use mid-level categories unless something is specified. Things like, if I say cat, I mean cats in general, rather than all felines in, living and extinct, or this particular cat that you've never met. Transitive properties, things like, if I ask you to pass me the book that's on the table, you won't necessarily be upset at me for giving bad directions if the book is on top of a tray that's on the table. We know what we mean. All of this boils down to humans having 2 kinds of thinking. Fast, error-prone, intuition-based thinking, which is really fundamental to human thinking, and slow, more accurate, rationality-based thinking, which is much more like computer thinking. So, computer thinking, the slower, rational kind of thing, is particularly good when it's supplemented by actual computers for problems that humans are not good at. So humans have given computers all kinds of human problems. Some have worked, some have not. Basically, it works best when computers get problems that we're not good at. Things like when working memory exceeds 7, or when it's highly complex or unstructured. When the best solution to a problem is really more important than the speed at arriving at that solution, and when reciprocal communication and interpretation is not assumed. Just to give you an example of how computer thinking and human thinking are different, I'm going to give you a sort of run through of what it's like to tell a human how to make a cup of tea, and tell you what it's like to tell a computer how to make a cup of tea. So if I ask a human to make a cup of tea, I say things like put the kettle on, put a tea bag in a mug, and the human can do that. Pour just boiled water into the mug, humans can do that too. Remove the tea bag, add a splash of milk, that's no problem. Enjoy! Great, that all worked really well. This human, which in fact is me, it's fine, was able to follow these instructions quite easily. But if you ask a computer to make a cup of tea, start out the same way, and the computer says, no, error, kettle not defined, tea bag not defined, mug not defined. So you just take a step back and you have to define those things. You say, right, that's an electric kettle, that's a mug, that's a tea bag. Are we all okay now? Yes, okay, now put the kettle on, put the tea bag in the mug. And the computer says, error, kettle cannot go on tea bag if tea bag in mug. And the human is now a little annoyed, but says, right, put the kettle on its base and turn it on. And the computer says, error, low water warning. Now, a human, even if there was not enough water in the kettle, would have just put water in the kettle and turned it on. You didn't need to tell the human that you have to tell the computer that, because it doesn't know. So the human says, put 250 milliliters of water in the kettle, return it to the base, turn it on. See, even now, the instructions are getting much more clear because the human is learning how it has to define everything and put it in order, short sentences, clear commands. Computer still says, error, water not defined. The human says, right, there's a tap, put 250 milliliters of water from the tap into the kettle, put the kettle on its base, turn the kettle on. Then put a tea bag into a mug. Okay? Computer has filled the kettle, put the kettle on, put a tea bag into a mug. Human says when the kettle indicates the boil cycle has finished, pour the water into the mug. But the computer pours water from the tap into the mug, because as far as the computer knows, we defined water as coming from the tap. It doesn't understand the sort of logical inference that we mean the water from the kettle. Computers don't know. They don't have inference. So the human by this time is super annoyed. It thinks, this is not worth my time. I do not need this. And we'll just break down why it's different. So humans have abstract concepts, inference, shared background knowledge, fuzzy categories, context dependence. I won't go too much into this, but that example shows how humans and computers think differently. Computers, concrete definitions, they only use things that you have defined. Nothing carries over from one scope to the next. Strict categories, it's absolutes. This comes out a little bit in how we have to give instructions about things. So humans, we accrue expertise over time, but generally you just give someone a citation list and you trust them to come to more or less the same level of expertise on the topic. We have mental models, and to share those mental models, we have debates and discussions, and we write out journal articles. Computers have defined equations and formula, misspelled formula. They have mathematical models, but these are clear and concrete and thoroughly defined. They can create charts and graphs and visualizations, but they cannot write journal articles. You need a really detailed methods section when you're working with computer methods. Just like trying to give the instructions to the computer to make tea, had to go step by step, clear, short commands, everything defined. You have to be careful. And computers use data sets and codes and things that you can define clearly. So the issue is why you need computational social science is that there are problems in the world that need both human thinking and computational thinking together. So for example, you need human thinking to identify the problem and possible solutions and relevant information. And you need computer thinking to work accurately and reproducibly with large volumes of complex data. So you might say, making 1 cup of tea is a human problem because we can just give, we know how to do it, we identify the problem solutions, we take care of it. But making 8 million cups of tea is a computer problem. That is, it will take us a long time to get the computer to make 1 cup of tea, but once we can get it to make 1 cup of tea, it will make 8 million cups of tea, no problem. That's about accuracy and reproducibility. So, these kinds of mixed problems that need both human and computer thinking are becoming more common because we have more resources are becoming digital, because people are using social media, because we have got smart kettles and smart fridges and everything is just becoming computer enabled. Real-time data is becoming available if we want to really access people's heart rates or travel paths or blood sugar levels if they've got digital glucose monitors. It's great, but it does mean that we have questions like this, social science questions like, how do people's travel to work change as a result of COVID-19? We need human thinking to identify the research question, identify possible things to explore. Do we mean right now, or 3 months, 6 months, a year, 3 years? We need human thinking to identify possible paths that might follow. Will people travel by bicycle or private car rather than public transportation? Will they wear masks on public transportation? What's the peak capacity going to be on public transportation? And, will they work from home 2 days a week, 5 days a week? We don't know, but it's interesting. We need human thinking to identify relevant resources, things like where can we get data on how people's patterns were in 2011 to compare, or the upcoming 2021 census. Both of those will include very detailed journey to work information. But in the meantime, maybe we want to look at some maps. We want to look at how people are traveling, making travel requests on Google or Apple Maps. We want to get some open data to see how these patterns are changing now, because there's maybe too much time between 2011 and 2021 to really see how people are responding to this now. To do that, we need some computational thinking about acquiring data, maybe using an API, scraping a website, creating some kind of app that harvests data or asks people about their travel plans. We need computers to do some good communication, because we would probably need an interactive sort of communication platform for these results, a website that you could drag and drop and zoom in on maps and things like that. We might need human communication to write up some journal articles, to make some policy recommendations. This is a mixed problem. Now, I'm going to pass it off to Dermot, who will cover sections 2, 3, and 4 of the Big Five, and I will see you again for number 5. Bye for now.
Thank you, Julia. I'm Dermot from the UK Data Service also, and I'm going to take you through the next 3 domains of being a computational social scientist: writing code, understanding your computational environment, and understanding and manipulating data. So to help you, we've provided a number of open source self-directed learning materials. So these are computational notebooks, which contain live Python code, some additional materials. We point to lots of free open source samples of code also. So let's focus on writing code, which to us is probably the most crucial aspect of being a computational social scientist. So it's the ability to write code using a programming language, and it can bring fairly substantial, even say enormous rewards to you as a researcher, being able to capture and process and analyze new big sources of data. So firstly, what is a programming language? In essence, it's a way of allowing you to issue instructions to your computer. So you as a human want your computer to perform a given task, and in order to do so, you use a programming language. So similar to a spoken language, there are grammatical elements, so you need to specify the commands correctly. In Python, the print command is useful for printing messages to the screen. If you misspell that or if you don't specify it correctly, it just won't work. So there are grammatical aspects, and there are syntactical aspects as well. If you want to scrape a website, then process the data, and then save it, if you use the save command, before you collect the data, obviously the rest of it then won't work, or that bit won't work either. So the command may be correctly specified, but it doesn't occur in the right place. And that's a syntactical element as well. So a programming language allows you to issue instructions to your computer, but there are rules you need to follow in order to do so. This can be a new area, and it can be quite an overwhelming area as well, particularly if you don't have some form of IT background. So like any new language, it is quite difficult at the beginning. There's no getting away from it. You'll be limited in what you can do until you develop your proficiency. So to kind of help you on your way, there's some kind of key terms that I think it's worth knowing. So programming language, as we've established, is a means of interacting with and issuing instructions to your computer. Programming then is the practice of using a given programming language. It's also known as coding. Code is the actual written down instructions that result from doing some programming. And then a script is a collection of code. So it's all of your code stored in a .py file if it's Python code, but you can store it in a txt file if you want, for example. A shell is just a tool that allows you to write and execute code. If you're familiar with R, if you've ever used that without RStudio, you'll know what I'm talking about. I'll give you a quick example. So here's my computer. I can launch Python through the command line. So this is the Python shell that I can access, and I can do I can do calculations. I can print messages. to the screen, etc. As you can see, this would be a tremendously cumbersome way of writing code, so that's why we use either notebooks, as I'm just showing you now, or TXT files or some sort of file. Debugging is probably something you've heard. It's the process of fixing errors or issues with your code, and testing then is the process of discovering those errors. So before we actually look at a practical example of some code that helps me in my own research, we should really think about how we should undertake our coding or our programming. So literate programming is quite a powerful approach. It's quite common nowadays. And it emphasizes that while computers take the code and act upon it, in reality, your code is going to be written, read, and adapted by humans. So therefore, your code has to be written in such a way that someone else can understand exactly what is happening. So not just the computer, but a human as well. So let's just look at two quick examples, one which we will call some literate code and some which we'll just call some very bare, unadulterated code. Both approaches work and produce the same result, but I'm sure you'll agree one will be much easier to write and to share. So let's make this a little bit bigger. So here I've got some code here. You can see I've run this before. Let's run it again. So this is live code. Okay, so it produces a result. So what I'm doing is I seem to be taking something into Python, something called requests. I seem to be creating a variable here, and it's equal to this, and this looks like a web address. I'm creating a second variable, and it's storing the results of something, some method here, and then I appear to be printing out the results. So this is an example of web scraping. It's, we're really scraping this website right here. But as you can see, even understanding, some Python code in general doesn't really allow you to understand what I'm trying to do here. So obviously, again, the computer clearly knows what's happening because it produces the result. But could you, as a human, actually understand what I'm trying to do? So this is the exact same little program I've written. This time, I've used some clear headers, I've used some line spacing to improve readability, and I've used descriptive variable names. So it's quite obvious now that this refers to a web page that I'm trying to scrape, and I'm clearly telling you that let's take a look at the results of the web scrape. So same results, but one is written in a much more legible manner, again using things like descriptive variable names, line spacing, and a clear conceptual ordering of what we're doing. So literate programming does not mean writing mountains of code or comments, simply that you keep the human reader and user of your code in mind as you program. So coding is becoming a very popular social research method. I'll get my big head out of the way a little bit, apologies. So it's an increasingly popular social research method. It's a way of, producing knowledge about the social world, and it's a way of intervening in the social world as well. So some common uses, collecting data from online sources, from Twitter, from Facebook, scraping web pages, Wikipedia, the Guardian API, lots of interesting sources of data. You can employ computational techniques for analyzing text data, so you can use sentiment analysis, natural language processing, text mining, all these terms you've probably heard. And you can share your research results as well using, maybe you create a Twitter account that automatically posts findings from your research whenever a certain term is mentioned. So learning to code basically, I think, is never going to be a waste of time. It's going to really transform your research, even if it's just getting access to data. Maybe you never do anything like machine learning or anything like that. Just getting hold of rich, previously unavailable data is really powerful. So an example from my own research, I'm trying to get data about Australian charities. There's a regulator's website, which we can take a quick look at. And it has a web page for the 60 or 70,000 Australian charities that there are. So here's the University of Sydney's webpage. I'm quite interested in getting information about who sits on the board of that charity. So the organization itself has a unique ID, but its web address, as you can see here, has something else. It's a longer sequence of numbers and letters. So what I need to do is, for every one of these, I need to find its web address. So I won't talk you through all of this, but basically I've written a function. So basically I've written a method that I can call whenever I need it that will take a charity's unique ID, and at the end will return me its website ID. And let's have a look at how that works right now. So I'm going to call on my function. So I'm going to run the code. Whoop. There's a good example. I never ran this code. So programming languages, again, tend to be sequential, and if you don't run it in order, it clearly doesn't work. So what I've done here is I've given it an organizational ID, a valid one, and then it calls on the function. So it goes and it downloads the web ID that I need, and if it's successful, it shows me the web ID, and if not, it tells me I couldn't find it. So again, this is live code. We can see it produces this web ID for this charity here. Let's say I pick something nonsensical, run it again, and exactly, it shouldn't find the ID for that charity. So that's just a really quick snippet of how useful programming is for me personally in my research. I wouldn't be able to get, I mean, I could manually go to all of these websites, and it would take quite some time. So programming has really opened up new research, some cross-national opportunities for me in my work, which is really good. So the point of this right now is not to actually teach you how to program. We've got a free set of online learning resources and videos to support you if you want to learn how to program. And we've pointed to a couple of other ones as well. So this is us right here. Codecamp is excellent. It's by King's College London. It's how to learn Python, right down to the nitty-gritty, exactly how the language works. It's fantastic. And there's a great free online PDF, How to Code in Python 3, which acts as a tremendous reference manual for anything you want to do in Python. So let's move on to our next section. So this is about understanding your computational environment. And you can see here as well, the advantage of using notebooks, so you can keep all of your code and all of your narrative in a single document, so we're not jumping around. So what do we mean by your computational environment? The first thing to say is if you're going to be a computational social scientist or researcher, you're going to have to spend a lot of time knowing where files are and how to refer to them, how to download software, how to configure software, how to download additional packages or libraries for your software, etc. It's a little bit technical, it's a little bit tricky, but it is a core area of being a computational social scientist. So what is your computational environment? Is simply a mix of your hardware, so the physical computer you're using to do your work, and more importantly, probably for us as social scientists, it's the software you use. It's which version of Python, which packages in Python you use, and which version of those as well. Where are all the files? If you and I are collaborating and we have the same version of Python, the same packages, but I don't have access to the data, or the data is stored somewhere differently on my machine, it interrupts the workflow. It makes collaboration and replication very, very difficult. So let's take a look at your file system. So it's critical that you do think logically and in an organized way about how you manage and store files for your project. We've all been there. 6 months later, please produce table 1.7 again. Please rewrite chapter 4. The journal comes back and says, reviewers' comments, can you please address these, for example? And you can't remember where the latest version of the journal article is. You can't remember the latest version of the data. Did you use a syntax file, or did you do everything through the drop-down menus, etc.? So you do need to think really critically and logically about your files, and that becomes so much more important when you do computational work also. So there's two ways of referring to files on your machine. So it's the physical location on your machine's hard drive is what we're interested in. And that can be referenced by the absolute path or the relative path. And I'll explain what both of those are using some examples. So let's make this a bit bigger. So the first thing we want to do is figure out where we are currently. and where we are currently on our machine and not in a global sense. So we can ask Python, right, where is the file I'm working with right now? As you can see, my code that I'm working with is in the C drive. So it's on my hard drive. It's in a folder called users, another folder called this, one called projects, and then in a folder called code. So now I know currently where I am on my machine. So we can take a look at what other files and folders exist. You can see some results already. That's because I've run this code before. So let's rerun it again just to produce up to the minute results. So I list all the directories in the current location. So here is the code book we're currently working with. There's a data folder, there's an images folder, and there's the other notebooks, as you can see. Right, so if we take the data folder as an example, let's view where that actually is using the absolute and relative path to that directory. So where is this folder literally or absolutely on our machine? So again, it's on the C drive. It's in all these folders and it's found here. And again, we can take a look using the absolute path to that folder, what's inside, and you can see a couple of data sets that we're going to look at quickly in the next section. We can also achieve the same thing using the relative path to the data. So you can see this time I haven't referred to it as C, projects underscore or / code / etc. Now I've just said, show me all the files in the data folder. And this is an example of using relative paths. So the little trick we've done is the dot and the / is basically shorthand for where we are currently. And just if we need a reminder of where we are currently, we can go back and we can just do again a quick check. So this is where we literally are at the moment. Basically, we don't have to type that out by using the dot and the / that's shorthand for where we currently are, and then look inside the data folder. Why am I spending time on this? Well, again, if you and I are collaborating across different machines, we're going to have differently named folders. You might have things on the desktop instead of the C drive. You'll have different folders. It might be in something called projects. You might call it something completely different. The point is, as long as the data folder is in the same location as this bit of code, then this will always work. This will work on my machine, this will work on your machine without having to specify the entire absolute path. And you can see how useful that becomes working across teams that have 2, 3, 4, even more people, especially nowadays with the the scale of some of the research that's being conducted on COVID-19, for example. Huge team members, if they're all having to set the absolute paths themselves manually so they can find the data, it just introduces the chance for errors, and it slows everything down. So the final thing is we'll take a quick look at the hardware and software components of your machine. So hardware, it's the physical computer, it's your CPU, your central processing unit, and these are the physical components that make up your machine. But really, as researchers, we're mainly talking about software. So what operating system do we have and how much memory do we have on the machine? What programming languages or software packages do we use? Do we use Stata or Python? If we use Python, which version? There's lots of different versions. If we use Python and we use modules for scraping websites, what version of the requests module, which we saw before, which version of that do we have? Do we have all the data files on our machine, etc. So let's just take a quick look at a snapshot of my machine quite recently. So I've got Windows 10 as an operating system. Most of this is not terribly interesting. I mean, this one is. So this is your available memory. This is also known as random access memory or RAM. You've probably heard of that. So I've got just over 8 gigs of RAM. So basically that allows me to process up to 8 gigs of information at any one time. Not entirely that, because other processes on your computer are using some of the memory. But if I had, a 50 gigabyte data set, I'm not going to be able to load all of that into Python or into R and work with it on my machine. I'd either have to take a small sample of it, or I'm going to have to host the data somewhere else and use a different machine. We're probably more interested in software and versions. So let's take a look at which version of Python I'm running. So you can see I'm running version 3.7, so it's one of the latest versions. Some commands only work with certain versions of Python. It's maybe not going to be a big issue for you, but it can introduce some errors if you have a different version to your collaborator. And the final thing is you can view all the installed modules on your machine. So as I said, the requests module, here it is what you use for web scraping. If you didn't have that on your machine, you wouldn't be able to run the code that we've run earlier, for example. So that's a kind of a quick whistle-stop tour of computational environments. If you're watching this on the 20th of May, next week on the 27th, we have a coding demonstration about setting up your computational environment for doing computational research. In the meantime, or in addition, there's lots of really good resources. This is really good about using notebooks. This is excellent. The Turing Way handbook is a fantastic resource for understanding your computational environment. So it's chapter 10. And we've also got a little guide if you're using Python of how to install and set up an environment on your machine. So let's finish with a quick look at some of the data issues you're going to experience as a computational social scientist. So you may end up using many of the same types of data sets that you're used to using. So if you use social surveys, you'll have a tabular data set. Every row will be a person responding to the survey, and every column will be a variable captured about that person. So we won't focus too much about acquiring data because we've got some other webinars about web scraping and APIs and text mining, for example. So we'll just jump into two key issues of being data literate. So you need to understand how the contents of the data set are stored. So you can think of this as the variable type, if that's what you're used to. So was the response to the survey captured as numbers? If you ask somebody about their income, was it captured using words? Did you allow someone to type in, TWENTYTHOUSAND, for example, or did you restrict them to actually typing in 20000? So is it stored as numbers or text? And then in the aggregate for the entire data set itself, how is it actually structured? So as I said, usually you might have rows of observations and columns of variables, but you may have network data where you have, and I'm going to make a bad attempt at drawing. So you have a node and then you have connections to the node. So that type of data doesn't tend to get stored in a tabular way. And there's lots of other structures as well. Websites are structured hierarchically as well, using something called XML and HTML. So data comes in lots of different structures, and you just have to get used to it. So as I said, for example, in understanding society, there's a question about total income, and it's stored as a number. So it's not categorical, it's not text, it's stored a person's income as a number. And why is that important? Well, if you know what it's stored as, then that determines what operations you can perform. So you can calculate average income, while if it was stored as a text, it makes no sense to calculate mean income. So I'll skip ahead of these ones because I think understanding that variables can be stored as numbers or text is something we're probably all a bit familiar with. So I'll skip ahead of this a wee bit. This just shows that if you store variables as integers, so whole numbers, you can do calculations. If you store variables as decimals, then also you can do calculations as well. String is a data type in Python, which is basically a piece of text. And if you have a piece of text, then you can perform certain operations as well. So one of those would be the replace method in Python is quite good. So if there's a word in your piece of text that you don't want anymore and you want to replace it with something else, you can call the replace method. If you want to split up a piece of text at a certain point, you can use the split method as well. And you can see the results of those two commands down here. So we had a string saying this is my correct string, and then we replace the word my with your, as you can see here, and then we split this string at the point here also. Again, all of this is in the notebook where we go into much more detail. I just want to cover some of the ones you mightn't actually be familiar with just now also. So Boolean is a data type that stores values that are either true or false, 1 or 0, yes or no. What they're really good for is determining if something equals something else or if a condition is met. So for example here, we can check if 10 plus 5 does equal the same as 14 plus 1. True, as you'd expect. So print the result is true, and we can use the type method just to actually check that it really is a Boolean variable. So for example, if we wanted to check whether my grade is above 40, again, made the classic mistake. So if my grade is 39, that's not above 40, so I get a message saying, unfortunately, back to summer school for you. But if my grade was 80, then congratulations, you pass. So that's an example of a Boolean. So if grade is above 40, then that equals true. And I can go into this part of the command. If it's false, then we enter this part of the code right here. So I'm going to skip to data types because you'll see, I'm going to skip to data structures. So this is when we look at a data set entirely. How is all of the data actually stored? Again, as I said, if you're a social scientist or probably anybody actually who doesn't really work with network data or text data, you're going to probably picture a table, and you're going to picture a row, and you're going to picture columns, and you're going to picture cells which contain values for those variables. So that's something we call a data frame in Python, and an OR as well, I think is the term. It's a rectangular or tabular data structure, and you'll often find it in files which have the file type comma separated value, so .csv. .csv is a common file format for data shared on the web. So let's look at a simple example. So we've got a data set about the financial information referring to Oxfam. So it's one of the large-scale UK charities. And as you can see, it's stored in a rectangular format. So here's Oxfam's 2018-2019 financial data. Here's its 2017-2018 financial data. But we can also look at how we could store the exact same information in a different data structure in something called JSON, JavaScript Object Notation. So this is a hierarchical data structure. It'll contain the exact same values and fields as we've just seen in the previous example, but it will store them differently. So let's just take a quick look at that. So if I zoom out a wee bit, here we've got an example of the data here. Actually, let's make it look a little bit better. So we can print the results instead. Yeah, that makes it, actually that hides the hierarchical. Okay, let's just look at it like that. So now we can see the exact same data. So all the values for the name field, all the values for its unique ID, and its financial year starting date also. So that just gives you, again, a quick example of how you can store the same data in different structures. And to be a computational social scientist, you're going to have to get used to handling data that's not really familiar to you. But again, it won't impede your research. You'll be able to do the same calculations. You just need to do a little bit different work to get the data in shape for your analysis. So I'm going to hand you back over to Julia, who'll take you through reproducibility.
Thank you very much, Dermot. I'm back, and I will cover the number 5 from our big 5 of computational social science, documenting and enhancing your workflow. As computational methods become more accessible, more people are going to demand access to the information they need to do your research on their own. That is to say, people want transparency, they want access to your data and to your code, they want to be able to reproduce your results. This is part of what makes science trustworthy, is that other people can get the same results. But it's also how science advances, how it progresses, how we move forward. Reproducibility, in summary, is about making your data and code available to rerun an analysis. But there's a bit more to it than that. Because Reproducibility is using the same analysis on the same data set to get the same answer. Replicable is the same analysis on a different data set to get a logically comparable answer. Robust is the same data set with a different analysis to get a complementary answer. And generalizable is a bit of all of this. It's developing a really solid method that can be applied to different sets in possibly slightly different ways to get understandable output. These are all important things, but what we need to know is there are 5 simple new rules for the sociological method. And now, especially from what you know from what Dermot said, some of these will be obvious, like this. Tell us about your software. We need to know what software packages you used. Tell us about your data. Tell us how to get it or provide it to us. Show us how you got your data ready. This one's a little bit more complicated. This is like if you downloaded your data from a source and renamed some of the columns or deleted some of them or maybe coded things into factors instead of using raw data. You have to explain that because it matters. Show us the analysis you did. Again, this is, pretty straightforward, but you do need to be very, very clear. So clear that a computer could understand you. People will be like computers and possibly you will think, how can you not understand what I said? But absolutely, be very clear. Finally, save all of your work openly if you can. That is to say, make your data sets, your actual data sets, and your actual code available to download wherever possible. If you're working with sensitive data, with personal data, with something that you're not allowed to share openly, then as clear as possible, tell people where they can go to get that data for themselves, or create a anonymized or dummy version or something that you are allowed to share so that they can test your method on that, and then maybe they will understand your method well enough to apply it to other data sets in the future. But share as much as you can, as openly as you can. Now, to help you do that, there's a few things you ought to know. There's a lot of technological tools and approaches to support your workflow. Writing code, for example, we've already talked about this. Using languages matters, but also your choice matters. Some programming languages are easily accessible, free to download, open source. Others are proprietary. So if you want to write in SPSS, a process in SPSS, someone has to have an SPSS license to use your process, whereas R is free to download. On the other hand, some people with very tight administrative control over their workplaces might not be able to download open source data software. They might consider that a risk, and so they are happy to pay for the SPSS license. What can you do? You just make the choices you make, justify why you make them. Know your computational environment and be as clear as possible so that someone else can replicate your environment, or at least understand how the differences with their environment might affect your code. Understand and manipulating data. Open data sources are great wherever possible, but they are not always. And so if you're using data that is sensitive or personal or protected in some way, you have to, as I said, make it clear how you got it. If you are using data that, depending on how you acquired your data, there may be limits to how you can use it. For example, you might be able to use it for academic work, but not commercial functions, or you might be able to use it with, you might only be able to use Twitter data, for example, if it's combined with certain kinds of geolocation data, but not other kinds of geolocation data. Pay attention to the end user license agreements, stay within the rules. Finally, documenting and enhancing your workflow. Things like Jupyter notebooks allow you to share your computational environment more or less, and so they can help others access your work directly without having to try and replicate your environment. GitHub is a collaborative platform that lets you store your data online in a repository, update it gradually. People can see the process of how it was updated. They can go back and see older versions and maybe look at the changes between them. They can contribute to it. It's great. It can be a little intimidating. We might do some more showing you how to access GitHub in the future. If you're interested, let us know. Finally, we've got some further reading. Most of these are about the thinking processes and why humans think the way they do and why that's different than computers, and how to deal with these kinds of limitations and workarounds that human thinking entails. Please let us know if you have any questions, if you have any insight, if you have suggestions for future work or resources that you'd like to see us discuss. You can send us emails, you can send us tweets. You can watch my Twitch channel if you like. That's where we do the coding demonstrations. And yeah, please do get involved. Further, here's some resources. Here's our GitHub repository for the new forms of data program of training. So for example, the code that Dermot worked through in 2 through 4 of the Big 5. You can find the Jupyter notebooks he was using, and you can sort of work right through them, and you can go back and you can edit and you can execute the code. Jupyter notebooks are really great. You can find this and other recordings of our webinars and trainings on our YouTube channel. The UK Data Service YouTube channel hosts all of our recordings. We have a help desk, so if you're trying to access UK Data Service resources and you get stuck, you can send us a help. You can subscribe to our newsletter to find out about webinars like this and other upcoming training events. You can subscribe to our tweets. You can join our Facebook group. You can, there's lots of ways to get a hold of us. We are here at your disposal. Thank you again very much for attending this webinar, and I hope it helps, and I hope to hear from you soon. Bye-bye.